Oh, okay, so like now we have three equations, right? One being the epsilon strain one, which relates U, and the other two being the moment and force balance, and the third one being Hooke's law, the constitutive relation. So like we can basically add them up. We have number of unknowns is equals to number of equation, 15 unknowns and 15 equation. So like what we can do is basically we can plug this equation into this equation to get a full-fledged equation for number one, like in terms of the displacement field u. So like we basically have this lambda plus u, gradient of u, and plus mu times Laplacian square of u plus f. So this is basically the heart of solid mechanics. Since like every time we need to know u, so like if we once know u, then basically we can calculate each and every other variable too very easily. Once we know u, and so that's why if we have u, then like we can find the solutions for this, and we can basically get solution uh, in terms of xy, and then basically we can get all the information, the stress, strain, and every other components due to this. So basically, now let's move to the discussion of boundary condition. So like to fully specify a problem, then like we also need to specify the boundary condition too. So basically, the boundary condition is basically of two types: the traction boundary condition and the displacement boundary condition. So the traction body boundary condition, at the traction boundary condition, we basically find some or like apply some load at that point, and while the displacement boundary condition is like where we say that it's fixed or not. So like for every PDA we need two things, that is the solution of PDA which should satisfy the boundary condition too. So like once we satisfy the boundary condition, then we can basically find the solution to it. So basically what we can do is we can initially start by writing out how we write boundary conditions. So like here is an examples in the note, which if you want to go through, then you can. Like it's a very simple example. Just one thing to keep note of is how we specify the traction boundary condition. Since like if we look closely, then like for this we are only given a traction or the force value at one phase. So basically, what we can do is we are given this traction, but we need a boundary condition in terms of sigma, so that we can then basically go ahead and basically guess the solution or like do any kind all kinds of stuff with it. So basically what we can do is basically we write the n cap, or so like for this case n cap is in the I had direction, so I write this at 10, and this traction is also as in the direction of, let's suppose it's a t and it's 0. So this is a traction. So basically now I have this kind of thing, so like where I can as you can see above, then like I have two conditions. So like I can basically write sigma and sigma, four sigma values, and then I can basically apply the matrix multiplication and basically get the solution in terms of this in any case. So like this is how basically we specified the boundary condition. So like a well posed solution problem in solid mechanics is basically that it should have some u that satisfies the field equation plus boundary condition, and there should be only one such u which in the end satisfies the field equation and the boundary condition, and it's basically the unique solution to our problem which we basically pose. So like this was for the video. So like for the next video we can start with the airy stress function, and then we can move on to the beam theory. So and with that we would end the course in a very simple and in a very easy way.